Here's example 31.2. A 400-gram cube is attached to a pin by a 30-centimeter string. The cube moves in a circular path on a frictionless table as shown. The cube has a constant speed of 2.4 meters per second. A. Draw a free body diagram representing the forces on the cube. B. What's the tension in the string? Okay, now here's what this situation is. Somehow there's a pin right here in the center of this table that is whirling this object around, this cube around on the end of a string. We're not worried about the mechanism by which that happens, we're just supposing that it does. We're looking at a bird's eye view, a top view of this situation. We're wanting to suppose that the cube is sliding on the top of the table. They tell us it is a frictionless table, so maybe you could think of this as an air hockey table, and I've got some cube that's being supported by this air cushion, and I've got this pin that's whirling it around. First of all, I need to draw a free body diagram. So I want to imagine taking this top view and turning it 90 degrees. What do I see? Well, first of all, I want to imagine that I'm taking a snapshot of this cube when it's at one side of the circle. And since your authors give it to you on the right side, then that's the side we're going to focus on. First of all, I'm going to show where the center of the circle is. Then I'm going to show the object on the right side of that center. There's my object in green. Now, what forces act? Well, I have the earth pulling the cube down, the weight force. I have the table pushing the cube up. That's the normal force. And now I have this string that's pulling on the cube. Which way does the string pull? Well, the string pulls it towards the center of the circle. I'm going to call that the tension in the string, Ft. And what I claim is that it is this tension force that causes the object to go in the circular path. And so when we say, what is the tension in the string, basically what we're asking is, what is the centripetal force that's acting on the object? It is that force that's causing the centripetal acceleration. Okay, so how do we find it? We're going to use Newton's second law. Newton's second law says that the centripetal acceleration is equal to the net centripetal force divided by the mass. Well, now which forces are causing the acceleration? Is it the weight? Nope. Is it the normal force? Nope. Those two forces certainly are acting on the object, but they are not causing the centripetal acceleration. The thing that's causing the centripetal acceleration is the string force, Ft. Now, I'm trying to find Ft. If I could get a number for the centripetal acceleration, they told me what the mass was, I could figure out what the string tension is. Say that force is equal to the mass times the acceleration. How can I find the centripetal acceleration? I'm going to use v squared over r. Now that I have an expression for the centripetal acceleration, I can equate these things together. And now let's solve that equation for the tension force. And let's feed in the numbers. And now plug those numbers into your calculator. Note that everything needs to be in MKS units, and don't forget to square the speed. I get that the string tension is right at 7.7 newtons. The tensile strength of a string is 90 newtons. This is the maximum tension the string can withstand without breaking. One end of a 1.0 meter piece of string is tied to a 4.5 kilogram toy car. The other end of the string is attached to a ring that is slipped over a pole. Neglect friction and determine the maximum velocity in revolutions per minute that the car can move around the circle without breaking the string. This situation is similar to the previous one, in which I have an object which is moving on a frictionless surface in a horizontal circle. A bird's eye view of this would look something like the following. Just for variety, I've drawn now the object on the left side of the circle. Now I want to rotate this and sketch a free body diagram of what's going on. So I've sketched the center of the circle, and I've sketched the object, and now I'm looking at it from the side. there are three forces that are acting. One of them is the weight force, the other one is the normal force, and the third force, the centripetal force, the force that's causing the centripetal acceleration, is the string force, and I'm going to call that the tension in the string. We're told that the maximum tensile strength of this string is 90 newtons. In other words, the string will break if I exceed 90 newtons. Let's figure out how fast the car can go. What is V when the tensile strength is exactly equal to 90 newtons? So let's use Newton's second law. The centripetal acceleration is equal to the net centripetal force divided by the mass. In this case, the centripetal force is caused by the string tension. Let me put that in. And I know that the centripetal acceleration is equal to V squared over R. So I can rewrite this equation. And let's solve this equation for V. That's what I'm trying to find. And now let's put in the numbers and feed those numbers into the calculator. And I find that the speed is roughly 4.5 meters per second. In other words, if I exceed 4.5 meters per second, my string's going to break. But now they don't want me to express the speed in terms of meters per second. They want it in terms of revolutions per minute. How am I going to do that? Well, basically what I'm going to recognize is the speed is equal to 2 pi r divided by the period. So let me figure out what the period is, the time for one revolution. And I'll feed in the numbers. And I'll put that into my calculator. And what I find is that the time for one revolution, the period, is just under 1.4 seconds. Let me recognize that the frequency is the reciprocal of the period. In other words, the frequency is the number of revolutions per second. And I know how many seconds there are per revolution, so if I take the reciprocal of that, I'll find that in revolutions per second. And then I can convert that into revolutions per minute. And now let me put the numbers into the calculator. And I find that this is just under 43 revolutions per minute. And you see I've changed my mistake. I find that there are just under 43 revolutions per minute. If I go faster than that, the string's going to break. If I go slower than that, then I should be okay. The string won't break. The last example involves a tether ball. Example 31.4 says a child swings a 1.2 kilogram ball along a circular path whose radius is 62 centimeters as shown. The instantaneous linear speed of the ball is 2.0 meters per second. Find the tension in the string. Well, now you can imagine this if you've ever been to a playground and played tetherball. I have some pole. This pole has a ball suspended from the top. And they're telling us that this ball has a distance away from the pole of 0.62 meters. That's the radius. The horizontal circle has a radius of 0.62 meters. Now, the ball is moving around and around in a circle. And this diagram here kind of shows a combination between a bird's eye view, because we can see the perspective of the circle, and the side view. I'm going to go ahead and sketch a Freebody diagram from this. What forces act? I claim that there are two forces. One of them is the weight force, and the other one is the tension that's in the rope that holds the tether ball to the pole. Now, if those are the forces that are acting, what is the force that's causing the centripetal acceleration? Is it the weight force? Well, no, because there's no component of the weight that is in the radial direction. The weight acts straight down. This is a horizontal circle. It is a component of the tension force that causes that. And if we break the tension force into a horizontal and a vertical component, I'm going to call one of them the radial component, and the other one is going to be the vertical component. It is the radial component of the tension force that causes the centripetal acceleration. So let's redraw this Freebody diagram over here to the right. And now I want to break this tension force into horizontal and vertical components, into a radial component and a vertical component. Now, notice I called that one component FTY, that vertical component. I've called the other one FT perpendicular because it's not only X, it's also got kind of some other coordinate as well. But whatever it is, it's perpendicular to the center of the circle, perpendicular to the pole. And it's this FT perpendicular that is going to be the thing that causes the centripetal acceleration. If I could figure out what FTY is and what FT perpendicular is, then those two are going to be parts of a right triangle. I'll have a horizontal and a vertical leg of a right triangle, and I can figure out what the hypotenuse is. How can I find the vertical component and the radial component of the force? Well, I'm going to use Newton's second law. First of all, let's write about the vertical things. Vertically, the ball is not changing its position. It's going to stay at the same vertical position, essentially. Moving in this circle, it's not going to move up, it's not going to move down, it's going to stay at the same level, basically the same distance above the ground. So I can say that the y component of the tension force is equal to the weight. And since they tell me that I have a 1 kilogram ball, I know that the weight is going to be m times g, 1.2 kilograms times 10 meters per second squared, or 12 newtons. So I've found one piece of this tension triangle. The vertical piece is 12 newtons. What about the radial piece? I'm going to have to use Newton's second law with centripetal acceleration. And I'm going to recognize that the centripetal acceleration is equal to v squared over r, and that the only force that's causing the centripetal acceleration is the radial force of the tension. And now I've got it. I can solve that equation for the radial component of the tension. And now I'll feed in the numbers. So now I put the numbers into the calculator. I find that the radial component of the tension is equal to 7.74 newtons. 7.74. Now, I need to find what the hypotenuse of that force triangle is. Let me resketch the force triangle. So I'm going to pull this down here just a little bit. And now I can use the Pythagorean theorem. And I'll put in the numbers and feed those numbers into the calculator. And I get that the tension force is 14.3 newtons. That's it.